Yeah, so recall we continue from where we left off yesterday. So yesterday we were talking about deformations with certain properties. We said that most of the times we are not interested in all the deformations, but we are interested in deformations having some fixed properties. And we said we said we said when a property is nice, we called it deformation condition. It satisfied some hypothesis, and we started with constant determinant deformations with constant determinant, deformations which are minimally ramified at a prime. And we ended our discussion yesterday with ordinary condition. So let me recall that. Suppose a rho bar from GQS to GL to F is a continuous, odd, and absolutely irreducible representation such that rho bar restricted to GQP is upper triangular with characters eta1 bar and eta2 bar on diagonals, and this eta2 bar is unramified character. So this is just a recall from where we stopped last time. But yesterday I made a small error. Like I assumed endomorphisms of rho bar to be scalars, but it turns out that the way I have formulated the ordinary condition, if you want the equivalence between the ordinary condition in our sense and ordinary condition that we know traditionally, we need this absolutely irreducible hypothesis. For reducible ones, which are non-trivial extensions of characters, the ordinary condition should be reformulated in a different way. It can be done using trace and determinant like I did, but the way I have reformulated it now, it should be we should have this absolutely irreducible assumption. So I'm just going to put it. This was an error that I made yesterday, so I've corrected it in yesterday's slides also. Okay, so rho bar B is such a representation, and so to formulate the ordinary condition, we first chose a lift G0 of frop P in GQP such that eta1 bar of G0 is not eta2 bar of G0. So because eta1 bar and eta2 bar are different, that's in our assumption, we can choose such G0. And let R be a CNLWF algebra, rho be a lift of rho bar to R. And we let B to be the unique root of the characteristic polynomial of rho G0 such that B is B modulo MR is equal to eta2 bar of G0. So this follows from Hensel's lemma that such a root exists and it's unique. And in this setup, we said that rho is ordinary if the following expression holds, and the expression is trace of rho of GH G0 minus B times trace of rho of GH minus determinant of rho of H times trace of rho G G0 plus B times determinant of rho of H times a trace of rho of G is 0. So it's a long expression, but this is like we have written it out, we expanded the brackets. So basically this is the trace of product of three matrices, rho of G times rho of H minus determinant rho of H times identity times rho of G0 minus B times identity. So once we have this, when we take the product of these three matrices, we said the ordinary condition means that the trace should be 0 for all G in GQS and H in inertia group. And when we expanded that thing out, we got this weird looking expression. Okay, and we wanted to know that, so we started this lemma which said that this ordinary condition is same as the ordinary condition that we know traditionally. So we call this ordinary condition and we denote it by odd. It's easy to verify. This is actually a deformation condition because we have formulated it in terms of trace and determinant. And for a CNLWF algebra, D rho bar of odd is just the set of deformations of rho bar to R which satisfy the ordinary condition. And this is the lemma where we stopped. That rho is ordinary in our sense, if and only if rho restricted to GQP is upper triangular with characters eta1 and eta2 on diagonals, which lift eta1 bar and eta2 bar, and eta2 is an unramified character. So this was the equivalent, right? I mean, we formulated a condition which seems a bit complicated, but it was in terms of trace and determinant. And it has this nice formulation in terms of classical language that we already know. We proved the backward direction, right? The reverse direction was very easy. We just computed rho of H minus determinant of rho of H times identity times rho of G0 minus B times identity. And this product turned out to be zero matrix because of this upper triangular shape. And so the ordinary condition was trivially satisfied. So we'll now see the forward direction. So to see the forward direction, we need to first observe that if we can change basis if necessary to assume that rho of G0 is diagonal with A and B on diagonals. So this diagonalization is an easy argument. It's not very hard. You once sit down and you see what you want to do, the proof is not very hard. You have to use a Hensel's lemma a bit, and otherwise the proof is rather easy. So that's the first step, that we can assume that rho of G naught is actually diagonal. And so if we denote rho of H to be AH, BH, CH, DH for H in inertia, we compute this product, rho of H minus determinant of rho of H times rho of G naught minus B, in this basis in which rho of G naught is diagonal. We get the matrix that I've shown, that we have these 2 0 entries in the second column. In the first column is AH minus determinant rho of H times A minus B times CH times A minus B. Okay, so you put G is equal to G naught in the ordinary condition. So that means that the trace of this matrix, this matrix that you see here, and the times G naught times rho of G naught is 0. So the product of this matrix and this matrix have trace 0. Actually, I could have just put identity. That would have been easier. But anyway, yeah. So the trace of the product is A times AH minus determinant rho of H times A minus B. But A and B are the roots of characteristic polynomial of rho G naught. So A minus B is a unit because they are not congruent modulo the maximal ideal, but they're distinct. That's our assumption. So this means that AH is determinant of rho of H because A and A minus B, A times A minus B is a unit. Okay. So now for G in GQS, we suppose rho of G to be AG, BG, CG, DG. And let G1 in GQS be such that BG1 is a unit. So we choose a G1 such that the upper triangular entry of rho of G1 is a unit. And you can always find it because our rho bar is absolutely irreducible. Because if there's no such G1, the reduction will become reducible, which we are not assuming. So we can definitely find such a G1. So we put this G1 in the deformation condition, and we already know that AH is determinant of rho of H. So in this product, the product matrix that we have got here, this upper entry is going to vanish. So this matrix is just 0, 0, CH times A minus B times 0. And so when you put G1 in the ordinary condition, that means that this product should have trace 0. And the product is just, the trace of the product is just BG1 times CH times A minus B. BG1 is a unit, A minus B is the unit we saw. So CH is 0 and H is determinant of rho H for all H in inertia group. So what we have proved is that the inertia group, the representation is upper triangular under the basis, but rho of G naught is diagonal under this basis that we have gotten. So it means that rho of G naught is diagonal, rho of inertia is upper triangular, and your GQP is generated by inertia and Frobenius. So rho restricted to GQP is also upper triangular. So it looks like eta 1 star 0 eta 2, because the A and B are chosen such that A is lifting eta 1 bar of G naught, B is lifting eta 2 bar of G naught. So from the choices, it follows that eta 1 and eta 2 should be lifts of eta 1 bar and eta 2 bar. And because we know that when you restrict it to the inertia group, the matrix is upper triangular, and we have proven that the upper triangular entry is determinant. So the the upper diagonal entry is determinant. So the lower diagonal entry should be 1, because it's upper triangular. And so we get DH is 1 for all H in IP, which means this eta 2 is unramified at P, and this proves the lemma. So the nice thing about this is that we can indeed formulate the deformation condition of being ordinary in terms of trace and determinant, which is really useful when we are dealing with the reducible representations. So that at this point we might come to it again towards the very end. So the ordinary condition can also be formulated for n-dimensional representations, but it's more complicated and it's not that easy to deal with. And I think Gerachtes' thesis had something to, he did some work on these ordinary conditions in a more general setting. Okay, so this was the summary of ordinary set, like various kind of deformation conditions that we can have. So we are going to move on and go on to the more arithmetic side. We are going to talk about R is equal to T theorems. So far, if you see, we were always on the algebraic side. We were always talking about deformation rings and various conditions on deformations and so on. But except the Galois group, there was no number theory as such involved. And we also developed most of the theory for a general profinite group. So we were really typically on the algebraic side. So if you want to go to arithmetic side, you need to involve some number theory somewhere. And so, for example, if you want to study which representations are arising from modular forms, or if you want to prove that some representations which have certain properties, they arise from modular forms, you need some kind of object to compare your deformation ring R with, right? Because R was interpolating all lifts of rho bar to any CNLWF algebra R. And if you want to say compare it with some arithmetic lifts or the lifts coming from arithmetic objects like modular forms, elliptic curves, and so on, you need an object which will interpolate all the lifts which are coming from such representations. And that thing is done by Heke algebra. So typically on the arithmetic side, the Galois representations attached to modular forms or more generally automorphic forms, they are usually interpolated by Heke algebra. So they are like the arithmetic analog of deformation rings. And an R is equal to T theorem, it basically compares a suitable deformation ring R with the Heke algebra T acting on a suitable space of modular forms or automorphic forms and asserts that they are isomorphic. So this is like a standard kind of theorem that has come to known as R is equal to T theorem. So if you want to prove that, say you have a lift of your rho bar to ZP or some finite extension of ZP, it has some properties, some nice 2-3 properties, and you want to prove that this representation is coming from modular form. What you do is you first take the deformation ring, which is a universal deformation ring with those properties. You put all those conditions are deformation conditions, and you get a deformation ring. And then you want to what kind of modular form it should arise from, if it is arising from. So you just take Heke algebra acting on all such modular forms, and you compare these two objects. And if they are isomorphic, you know that all the lifts are modular, because all the maps from R to a finite extension are just the maps from T to finite extensions, which will give you modular forms. So that is like the basic idea. So an R is equal to T theorem, it has 2 steps, you can say. Like, first of all, based on the deformation problem, you have to choose a suitable R and construct a Galois representation over it, which satisfies those properties. If you want a map from R to T, you first need to construct a deformation of your residual representation having those properties. So that is the first step. And the second step is this Galois representation or deformation. It will give you a map from R to T, and you have to then you have to prove that it's an isomorphism. So usually, not always, but usually this construction of Galois representation is not that hard. Usually, I'm not saying always, but in nice enough situations, getting this Galois representation is a standard argument, more or less. Maybe proving properties could be tricky, but I guess the real difficulty more or less always lies in proving that this map is actually an isomorphism. Till then, things are smooth, you can say. But again, it depends from situation to situation. I don't want to generalize anything. Okay, some historical significance of this is that a key step in the proof of Fermat-Glass theorem, it was an R is equal to T theorem in the setting of modular forms of weight 2. We'll see it later today. And these theorems have also played a crucial role in many important results, like the modularity of elliptic curves, which is due to first Wiles and then Breuil, Conrad, Diamond, and Taylor. Proof of sets conjecture, which is due to Curry and Winter-Berger, which said that every odd irreducible two-dimensional representation of GQS, it arises from a modular form of fixed level weight Nepentipus. And also Sartoudet conjecture due to Clauzel, Harris, Taylor, and others. So in all these major breakthroughs in number theory that have come in past 3 decades or so, the modularity, the R is equal to T theorem has played a crucial role. So we'll start with the modularity theorem, which is like we'll start with an R is equal to T theorem, which is the first R is equal to T theorem proved. It is due to Mazur. So this was in his original paper on deformation theory. So let's look at this R is equal to T theorem. So let's first describe the setup. So let P be a prime greater than or equal to 5. Rho bar be this representation from GQP comma infinity to GL2 of FP. We assume it to be odd and absolutely irreducible, but it has more conditions that we'll now describe. So first of all, we want rho bar to be induced from a character of GKS prime, from an unramified character chi bar of GKS prime. So K is Q adjoint with square root of -1 times P, -1 over P minus 1 upon 2 times P. So this is the quadratic extension in which only P is ramified. S prime is the set of primes of K which lie above P comma infinity, and rho bar is induced from an unramified character. So it's unramified everywhere of GKS prime. So, and we assume the image of rho bar to be the dihedral group of order 2H with P not dividing H. So the image is rather small. I mean, because it is induced, the projective image is going to be dihedral, but we want the actual image to be dihedral as well. The dihedral extension L of Q, which is fixed by kernel of rho bar, it has class number prime to P. And H2 of GQ P comma infinity of at rho bar is 0, or in other words, we want rho bar to be unobstructed. So this seems like a lot of conditions, but I'd like to recall that we have already seen representations which satisfy these properties. They are the neat S3 representations which were constructed by Mazur. So I think in the third lecture, we were looking at examples of unobstructed representations. And these representations, there's a family of representations that Mazur constructed, right? The splitting field of x cubed plus ax plus 1 such that 27 plus 4a cubed is a prime. We called them neat S3 representations. So those representations, they actually satisfy all these properties. So, you know, these are not just properties that are not satisfied by anything. We do have a bunch of examples. So if the properties seem too complicated, you can just assume that we are working with this neat S3 representation, and that's fine. And one thing to note is that because this character is unramified, the image of inertia and image of the local Galois group, they are the same. So rho bar of IP is rho bar of GQP, and rho bar restricted to GQP is factors through a totally ramified quotient of GQP of order 2. And under a suitable basis, this non-trivial element is -1, 0, 0, 1. So the quadratic extension is the extension where P is ramified, and after that everything is unramified. So we get this from that right away. So because of this, we know that rho bar restricted to GQP looks like sum of two characters. One is a trivial one, and the other is a character corresponding to totally ramified quotient of GQP of order 2. So in particular, rho bar is an ordinary representation, because in our definition, ordinary meant that it's a sum of it's an extension of two characters, and one of the character appearing on the lower side of the diagonal is unramified, and so this is satisfying that. So rho bar is ordinary, so we can talk about ordinary deformation ring of rho bar, and that's what we are going to do next. But before that, one small observation is that we let rho from GQP infinity to GL to ZP with a unique lifting of rho bar such that image of rho and image of rho bar are the same. They are the same dihedral group. And this lift is ensured by Schur-Zassenhaus theorem. So this is a classical theorem from group theory. Because the image of rho bar is not divisible by P, the sequence that you get from GL to ZP to GL to FP, when you just restrict it to the dihedral group, the sequence will split. So you get a map from this dihedral group to GL to ZP, and that is because I think it's a theorem about pro-P groups by Schur-Zassenhaus. I forget the proof, but it's a classical theorem. So there is always this unique lifting. It can be thought of as like the Teichmüller lift of a character. This is like a similar to that, but in 2 dimensions. And it only happens because P is not dividing the image of rho bar. Otherwise, this won't happen. So there is this lift, and it is giving us a representation with finite image. And the classical theorem of Heke tells us that this rho is actually the p-adic Galois representation attached to a cuspidal Heke eigenform F0 of level, it should be gamma 1 of P, not gamma naught, it's a typo, I will correct it, of level gamma 1 of P and weight 1. So this is a classical construction of Heke, theta series. You take the theta series corresponding to the Teichmüller lift of the character chi bar, and you get this eigenform. So there is a weight 1 eigenform which is coming from gamma 1 of P and weight, which is coming from this lift rho of rho bar. And this F, it has UP eigenvalue 1, which means it is also ordinary. And because it is ordinary, by Hida's theorem, we have an ordinary lambda-adic eigenform F of level 1 and some character chi, which specializes to F0. So there is a Hida family passing through this eigenform not, which means that there is an ordinary lambdatic eigenform. If you remember this, we defined this in our second lecture. So this ordinary lambdatic eigenform is kind of it's an eigenform which is interpolating various ordinary eigenforms. It's like a family of ordinary eigenforms, and so we have such a family which is passing through F naught. So this will give us the Heke algebra we want to work with, because and then we'll talk about deformation ring. So let T naught be the lambda Heke algebra, which is acting on the space of ordinary lambdatic forms of level 1 and character chi, which is generated by the Heke operators TL for L not equal to P and UP over lambda, because level is 1, these are all the Heke operators. And F naught, it will define a prime ideal P naught of T circ, right? Because this T circ is the lambdatic eigenform F defines a minimal prime of T circ, and because when we specialize to F naught, it will define a prime ideal P naught, which is containing this minimal prime, such that T circ modulo P naught is just ZP. And we let M be the maximal ideal of T circ, which is generated by P and P naught. And we let TM circ to be the completion of T circ at M. So this is the Heke algebra we want to work with. We cannot just work with T circ because we want to compare it with the deformation ring. And first of all, we should have some Galois representation over it. And for that, we have to first make it into a CNL WF algebra, right? Or CNL ZP algebra in this case. Otherwise, we cannot compare it meaningfully with our deformation ring. And for that, we have to choose a maximal ideal and completion. And this is the natural maximal ideal to choose, because we need a lift of the residual representation. And key ingredient to compare this comes from a theorem of Mazur and Wiles, that there exists a continuous odd irreducible representation rho from GQP infinity to GL2 of TM circ, such that rho is a deformation of rho bar. Determinant of rho is kappa times chi psych, where this chi psych was defined again, so like a cyclotomic character taking values in lambda. And trace of rho of Froebel is TL for all primes L not equal to P. Rho restricted to GQP is ordinary, in the sense that it is again upper triangular with characters eta 1 and eta 2 on diagonals. Eta 2 is an unramified character of GQP, and eta 2 of Frop P is UP. So basically we are getting an ordinary deformation of rho bar to TM circ. This is similar to the theorems of Hida and Wiles that we had recalled in our second lecture, where we got a representation over the total fraction field. Or when we fixed a prime and we went to the fraction field of TM modulo that prime, and we had a representation. But here we actually get a representation over the ring itself, which is crucial. So this theorem sort of tells us that this is the right Heke algebra that we have been looking for. And let R rho bar ordinary with the ordinary deformation ring of rho bar with maximal ideal M naught. So this is because rho bar is ordinary, we can talk about ordinary deformation ring. And because we have constructed an ordinary deformation rho of rho bar taking values in TM circ, this deformation will give us a morphism phi from R rho bar R to TM circ. Okay, and the theorem of Mazur says that the morphism phi, which is induced by the representation rho, is an isomorphism, and both rings R rho bar odd and TM circ, they are both isomorphic to ZP power series in one variable, so ZPT or the Iwasawa algebra lambda. So this is like, as I said, this is an R is equal to T theorem. We first chose a specific Heke algebra. We proved first, not we, but Mazur and Wiles proved that there is a ordinary deformation, which gave us this map, and then Mazur proved that this is actually an isomorphism. And both are nice rings, which are just power series ring in one variable. The proof is not very hard, so we are going to look at it a bit quickly, but it's not hard because the representation that we are working on is very nice. So what we'll first do is that we'll compute the tangent space of our ordinary deformation ring. And we'll prove that the tangent space mod P, it has dimension at most 1. There is a question, I guess. Has this been generalized to totally real fields? So Mahesh is asking. I don't know. The proof that we will see is going to be very explicit. It works for this this specific, what you can say, this specific case in a sense. So, but I think there are these theorems of Fujiwara, right? There is an archive article of Fujiwara which gets quoted. So I think it has some R is equal to T theorems for totally real fields, but I don't know under what assumptions and what exactly. Yeah, so I was saying that what we are going to do is we are going to compute the tangent space dimension of ordinary deformation ring, and we are going to prove that the tangent space dimension of the mod p tangent space dimension is at most 1. We want to prove that dimension fp of m naught modulo p comma m naught square is at most 1. And to do this, we are going to see what kind of like the dimension of the ordinary deformations of rho bar to f epsilon, and we'll prove that that space has dimension at most 1. And to do that, we first note that at rho bar is actually, it has a nice form. It is 1 direct sum chi naught direct sum v, where v is some irreducible representation of a dihedral group. Because our representation is induced from a character, this structure of at rho bar is very easy to compute. 1 is just the trivial character. Chi naught is the character corresponding to the quotient of a dihedral group of order 2, and V is some irreducible two-dimensional representation. So we have this nice decomposition of at rho bar coming from dihedral group. And we should note that this sub-representation, 1 direct sum chi naught of at rho bar, it corresponds to the subspace of diagonal matrices of M2FP. So the diagonal matrices, because our representation is induced from a character, the diagonal matrices, they actually give a sub-representation. And just check that that when you conjugate diagonal matrix, you'll get a diagonal matrix again, because your representation either contains anti-diagonal entries or diagonal entries. This space is giving us the sub-representation 1 direct sum chi naught. So if rho prime is a non-trivial deformation of rho bar to GL2 of f epsilon, then rho prime corresponds to an element coming from H1 of this sub-representation 1 direct sum chi naught. If and only if rho prime is also induced by from a character chi prime which is deforming chi bar. This is a crucial observation, that because at rho bar it has this direct sum, the H1 of at rho bar is also going to split into H1 of 1 direct sum chi naught plus H1 of V. And we know every deformation rho prime to f epsilon of rho bar, it comes from an element of H1 of at rho bar. So that deformation, it comes from this sub-representation, H1 of this sub-representation, if and only if the deformation itself is induced by a character chi prime, and where chi prime is lifting chi bar. So this is a very rather easy observation. But what does this tell us? That if the class number of k is co-prime to p, right? Because the class number of L is assumed to be co-prime to p. So chi prime is ramified at the prime of k lying above p. This character chi prime, if your rho prime is coming from an element of 1 direct sum chi naught, it is induced by a lift chi prime of chi bar. And this chi prime is ramified at the prime of k lying above p, because the class number of k is assumed to be co-prime to p. So such a deformation is never ordinary. That's kind of the main point. That if you have a deformation coming from a lift of induction of a lift of a character of chi bar, that is never ordinary. So we have sort of inside our tangent, inside our space of deformations to f epsilon, we have identified a subspace which does not intersect with the ordinary subspace at all. But because we are assuming that rho bar is unobstructed, the dimension of H1 of GQP infinity at rho bar is 3. And it is easy to calculate because this chi naught is odd, and it is easy to calculate H1 for 1. It is easy to calculate the dimension of H1 of GQP comma infinity of 1 plus chi naught. And that dimension turns out to be 2. So inside this 3-dimensional space of deformations of rho bar to f epsilon, we have identified a 2-dimensional space which has no ordinary deformations. So the space of ordinary deformations has dimension at most 1. It cannot be more than 1. This proves the claim that we wanted to prove. So what it means is that that our ordinary deformation ring is a quotient of a power series ring in one variable. Now we analyze this map phi, which is going from ordinary deformation ring to the Heke algebra. So if rho odd is the universal ordinary deformation of rho bar, then rho is just phi of rho odd, because rho is the ordinary deformation over Heke algebra, and by definition of phi, phi takes rho odd to rho, because phi is the map induced by rho. Now if L is not a prime, then TL is just trace of rho of Froebel, which is same as phi of trace of rho odd of Froebel. And if rho odd restricted to GQP is chi1 star 0 chi2 with chi2 unramified at P, then phi of chi2 of Frob P is just UP, right? Because the similar description over Heke algebra, we know that the bottom character gives UP when you apply Frob P. So therefore, when you apply phi to chi2 of Frob P, you get UP. So what is this telling us? This is telling us that the image of phi, it contains all the Heke operators which topologically generate Tm circ over ZP. And because this map phi is a map of CNLWF algebras, it is continuous. And so phi is surjective from R rho bar to Tm circ. This map phi is surjective because it is continuous. Okay, so we have found this, we have proved that this phi is surjective. We have proved that the dimension of the mod P tangent space of R rho bar odd is at most 1. Because this mod P tangent space has dimension at most 1. We have a surjective map G from power series ring in one variable over ZP to R rho bar odd. We compose it with the surjective map phi. We get a surjective map phi composed with G from ZPT to Tm circ. So we have this map, but we have a theorem of Hida which says that Tm circ is a finite flat algebra over ZPT. Well, that just means that if a phi of G is an isomorphism, and so both phi and G are isomorphisms, which proves the theorem. This is like a standard argument which is nowadays used in eigenvarieties, for example. You have this families of automorphic forms, you want to prove smoothness at a point. This is the typical argument that one uses. You identify deformation problem, you calculate the tangent space of the deformation ring, you give an upper bound, and then the local ring of the eigenvariety has the corresponding lower bound, and so they are the same, and the eigenvariety is smooth. So this is like a very natural argument, and even though this argument is old because it appeared in Mazur's original paper, it is still relevant even in modern studies, especially, as I said, of eigenvarieties and so on. And it's a very simple argument to understand, so I thought like it's good to give it. So in this way, just using some simple observations, you prove that the tangent space is less than or equal to 1, which gives a bound on the size of R rho bar odd, and there is already a bound, a lower bound on the size of Heke algebra, and so these bounds match, and we prove that they are the same. So this is like an R. So this is a deformation ring of rings of dimension 2. So you can call it medium R is equal to T. Now, why I'm saying medium? I mean, this is not a standard terminology. It's just I'm saying it because the theorems also come in various shapes and sizes. Like you can fix weight also, and you can get a R is equal to T theorem, which we call small R is equal to T, when T is actually acting on Heke algebra on modular forms of fixed weight and level. So that's what we'll see now. And then there is a big R is T theorem, which is between big rings, and we'll see why they are called that. So let's look at quickly a small R is T theorem. We are not going to state the proof, but this is this is like a special case of Taylor-Wiles and theorem of Taylor-Wiles and Diamond. So let P be an odd prime, F be a finite extension of Fp, and rho bar be an odd irreducible representation, such that rho bar restricted to GL is absolutely irreducible, where L is Q attached with square root of -1 power P minus 1 by 2 times P. This is the usual quadratic field we saw. Rho bar is arising from a modular form. That means you take a periodic Galois representation attached to a modular form, you reduce it modulo the maximal ideal, you get rho bar. Rho bar restricted to GQP is ordinary. That we just saw the notion, which means that rho bar restricted to GQP is upper triangular with distinct characters on diagonals, and the bottom character is unramified at P. And if L is a prime at which rho bar is ramified and rho bar restricted to GQL is reducible, then rho bar is minimally ramified at L. So by minimally ramified at L, we saw this in the last lecture. It means either the rho bar of inertia is either unipotent, 1 star 0 1, or it is a sum of its diagonal with distinct entries on diagonal. So it's like some character chi on one diagonal and 1 on the bottom. So if that is true, then it is called minimally ramified. Okay, and we choose S to be the, so we initially started with a representation of GQ. So we choose now a set S of primes L such that rho bar is ramified. And we also include P and infinity. So we consider rho bar as the representation of GQS. And we let determinant of rho bar to be epsilon times omega P power K minus 1. And epsilon is a character which is unramified at P. Question. Is anything known if bar eta 1 is bar eta 2? So if bar eta 1 is bar eta 2, the ordinary deformation problem is not well defined in the traditional way, because you have to make some choice which becomes, it is canonical when eta 1 bar and eta 2 bar are not same, but when they are same, things get tricky. You cannot always define an, what you can say, an ordinary deformation problem. But this trace determinant thing, it gives us an advantage of defining it in those conditions as well. So like Calgary-Spector and all the paper of Calgary-Spector, they sort of try to combine this case where eta 1 bar is also eta 2 bar, but they are in weight 1 mostly. But yeah, the main problem with eta 1 bar and eta 2 bar being same is that you cannot define the ordinary deformation problem. Like in the traditional sense, the trace determinant variant can still be there, but in traditional sense, you cannot. So I'm not sure if there are any results at all. The only thing I can think of is Calgary-Spector, but it is for weight 1 and it still does not prove R is equal to T. Okay. So we are in this setting. There is some more notation that we need to develop. So let N be the Tay-Martin conductor of rho bar. This is just a technical term. It's made up of primes at which rho bar is ramified, and the exponent depends on how ramified rho bar is at L. So if L is a prime at which rho bar is ramified, the exponent of L appearing in N depends on how deeply rho bar is ramified. Okay, let O be the ring of integers of the finite extension of QP, which contains Heke eigenvalues of all eigenforms of level NP and weight 2. So we are doing this so that we can define deformation ring and Heke algebra that we want to compare. So we first let R rho bar be the universal deformation ring of rho bar in the category of CNL O algebras. So we are taking this O rather than W of F usually. So the deformation, everything is set up in the same way. It's just that instead of taking power series over WF, we take power series, quotients of power series over O. And this deformation ring, it parameterizes deformations of rho bar, which are ordinary, which are minimally ramified at primes P at which rho bar is minimally ramified. We saw this in the last lecture. Minimally ramified means that if rho bar restricted to IL is just one direct some character, then image of rho and rho bar should be same. And if rho bar restricted to inertia is unipotent, then rho restricted to inertia should also be unipotent. And it has determinant epsilon hat omega P power K minus 2 hat times chi P. Chi P is the periodic cyclotomic character, and this hat is the Teichmuller lift. So if you see, this is a very nice thing, because these are the three kind of conditions that we saw in the last lecture and initially in this lecture. And this theorem is sort of combining all the conditions. You are putting all those conditions on our deformation ring to get R rho bar. So this is actually kind of a nice way of revising what we were doing. So this is the deformation ring. And now we define the Heke algebra. So for that, we let S2 of NP comma O with a subspace of modular forms of level NP and weight 2 with Fourier coefficients in O. Now we consider its submodule, O submodule S2 circ NP comma O, which is generated by the ordinary eigenforms of level NP and weight 2. Because all the eigenvalues are in O, all these things we can do. And we let T be the subalgebra, O subalgebra of the endomorphism ring of these ordinary eigenforms, which is generated by the Heke operators TL and diamond operator L for all primes L not dividing NP. So this rho bar will define a maximal ideal M of T, because this rho bar is coming from a modular form. And I think this Serre's epsilon conjecture, which is proved by Ribet, maybe and some more argument, it will tell us that it will come from an eigenform which is ordinary of weight 2. So that will give us a prime ideal, and when you go modulo the maximal ideal, you get maximal ideal of O. We get the maximal ideal M of T, which is defined by rho bar. Or in other words, rho bar is coming from a mod P modular form of weight 2 and level NP, and this maximal ideal M corresponds to that mod P eigenform, if you want that way. So let Tm be the completion of T at this maximal ideal. So Tm is now a finite and flat over O. And so this is the Heke algebra, this is the candidate. And we can just glue periodic representation attached to ordinary eigenforms of weight 2 and level Pn, which lift rho bar. And we get a deformation rho from GQS to GL2 of Tm, which is lifting. And it can be proven that this is ordinary, minimally ramified at all prime cell at which rho bar is minimally ramified. And it has determinant epsilon hat omega p hat power k minus 2 times chi p. So it is of the form that we need. So it induces a morphism phi from R rho bar to Tm. And the theorem of Taylor, Wiles, and Diamond says that if we are in the setup as above, this morphism is an isomorphism of local complete intersection rings. So this is an isomorphism, and because Tm is flat and finite and flat over O, it has Krull dimension 1. So these are small rings. Like in Mezu's thing, we saw rings of dimension 2, and here we are seeing smaller rings of dimension 1. So this is the so Taylor and Wiles proved. So the hypotheses are a bit weaker. We are putting a bit stronger hypothesis. The theorem is true under slightly weaker hypothesis, but I don't want to recall them here. This was first proved by Taylor and Wiles while proving Fermat's theorem. So this is like the key step in Fermat's theorem, this kind of R is equal to T theorem. And Diamond improved them by improving the Taylor-Wiles method. So the famous Taylor-Wiles method was introduced here to prove this R is equal to T, and the isomorphism of local complete intersection rings. And Diamond modified their method so he could weaken some of the hypotheses. So that's why I'm attributing it to both of them. So there are many small R is equal to T theorem, but you can say that this was like kind of the origin of R is equal to T theorem. Now we move on to big R is equal to T theorem, because it's natural to, like, we are putting some conditions on deformation rings and we are getting some Heke algebra. So it is natural to ask, what if we don't put any conditions on deformation rings? Just take the usual universal deformation ring of rho bar and ask if there is a Heke algebra which compares to that, and the answer is yes. That's what we are going to see next. The big R is T theorem. So again, a setup is the same notation actually, that P be a prime, F be a finite extension of Fp, n be an integer such that P does not divide n times phi of n. It's the Euler function. S be the set such that of primes L dividing n and P and infinity. Rho bar be a representation from GQS to GL to F, which is absolutely irreducible, and it is coming from a modular eigenform of level n. Now we introduce the Heke algebra. So the Heke algebra Tn is the big Heke algebra. So it is acting on modular forms of level n with coefficients in W of F and all weights. So it is, we are not fixing weights or anything. It is acting on everything. So it is the subalgebra of the WF endomorphisms of this big space of modular forms of level n, coefficients in W of F of all weights. And it is generated by the Heke operators TL and diamond operator L for prime cell not dividing P for W of F. And this representation rho bar, it is arising from an eigenform of level n. So it is going to give us a maximal ideal m rho bar of Tn, like the way we just saw in the previous case. And we let Tn rho bar be the completion of Tn at m rho bar. So it is just inverse image of T of n modulo m rho bar power n. Now, this is the Heke algebra. And it is, again, you can just glue all the periodic Galois representations, which are lifting rho bar of level n, periodic Galois representation attached to modular forms of level n, which are lifting rho bar. You can glue all of them. Get a deformation rho from GQS to GL2 of Tn rho bar of rho bar. So to this Heke algebra, there is a deformation. So there is this big map phi from R rho bar unif to Tn of rho bar. And we want to prove this is an isomorphism. So the first theorem in this direction was by Gouvier and Mazur. They said that if rho bar is unobstructed, this map phi is an isomorphism, and both rings are isomorphic to a power series ring in 3 variables. So that's why this is called big R is equal to T. We are not putting any restrictions on any deformation ring or Heke algebra, and the ring is becoming really huge. It's like a power series ring in three variables. So this is so it has crude dimension 4, and that's why we call it big. Big R is equal to T. So it is so this was like this is where the famous Gouvier-Mazur infinite Fern argument was introduced. So the key step in this proof was proving that Tian rho bar has crude dimension at least 4, because rho bar is unobstructed. We know that R rho bar universal is a power series ring in 3 variables. And if we know that this Tian rho bar, I mean, proving surjectivity of phi, so proving surjectivity of phi is easy, like the way we did last time, but proving it to be isomorphism, we need to prove that Tian rho bar is has at least crude dimension 4, so that it's at least as big as a power series ring in 3 variables. And that's what Gouvier-Mazur proved. They proved that Tian rho bar has crude dimension at least 4, and for that they used the Coleman's families of modular forms. So Coleman had developed a theory of periodic families of modular forms, and using that, they kind of gave a Fern-like structure inside Tian of rho bar. You just take a point and you have a family passing through it. And on infinitely many points there, they found some families passing through each of them, and they were not the original families. So you get a Fern-like structure, and when you because you have one horizontal line, and then you have some vertical line. So it's like a Fern-like structure, and when you complete the picture, it looks like a mesh or a net. So that gives like 2 dimensions inside Heke algebra. But they are all coming from modular forms. So when you twist them by deformations of characters or Tate twists, you get another direction, and that's how they proved that it has dimension 3. Sorry, it has relative dimension 3 over WFF, so at least dimension 4. So this is like a very, very quick summary of Gouvier-Mazur argument. And these theorems, this theorem was extended by Böckler under some mild hypothesis, which we call Taylor-Wiles hypothesis. So it's kind of the same hypothesis that we had in our small r is equal to T. That he proved that under some mild hypothesis, the morphism phi is an isomorphism. So he was not assuming that rho bar is unobstructed. So this is already, so he kind of improved Gouvier-Mazur result. And because Gouvier-Mazur infinite Fern argument worked for any Tian rho bar. It didn't assume that rho bar is unobstructed. So he already had in his hand that Tian rho bar has at least crude dimension 4, but now he's not assuming that rho bar is unobstructed. So his universal deformation ring is not a power series ring anymore. So he developed a new technique. He used those small r is equal to T theorems, and he compared big deformation ring with small deformation ring, and he got this isomorphism. And if you want, like as a corollary, it kind of says that if one of the previous theorems hold, and if you have any lift from GQS to GL to WF of rho bar, then it arises from a periodic modular form of tame level n. So this was like one of the questions, right? If we have any lift of our residual representation, is it arising from any arithmetic object? This big R is equal to T theorem tells us that it is arising from a p-adic modular form, which is not a classical modular form, but like a p-adic limit of classical modular forms. So this is a really big space that they have. Okay, so this has this nice arithmetic significance, and it is also an important tool in Emerton's strategy of proving Fontaine-Mazur. And I should say that this big R is T theorem is already been extended to n-dimensional representation coming from polarized automorphic forms, and also to Hilbert modular forms by Patrick Allen, using similar techniques to that of Böckler, but he extended the, what you can say, he modified the method a bit, so that it can work in higher dimensions or in more general setting. So this was an example of, these are 2 examples of big R is equal to T theorem. So that's all from me for for R is equal to T theorems. Now I still have 10 minutes and I still have something to say, and that is future directions. So we were looking at deformation theory, and we were only looking at, so from by Mazur's theorem, we know that the universal deformation ring exists as long as rho bar is absolutely irreducible, or the endomorphisms give you scalars. But there are other representations, right, which do not fit this criteria. So what about them? What if I want to study their lifts, because they also arise, like reducible representation arise all the time from modular forms. So we would like to study their lifts as well, and it is not always practical to have a representation which has endomorphism only scalars at hand. So there are two directions that one can take. One direction is the frame deformations. This was developed by Kissin. So we let rho bar be a continuous representation, no other hypothesis on rho bar, and we suppose G satisfies the finiteness condition phi p, which we had initially. And now we have this d rho bar square. This is the functor from category C of CNLWF algebras, the category of sets, which sends a CNLWF algebra R to the set of lifts. So in Mesure's theorem, we were looking at a functor which sends rho bar, which sends R to the equivalence classes of lifts of rho bar to R. But this is in this thing we are just sending it to lifts. We are not sending it to equivalence class. And the theorem of Kissin was that this functor d rho bar square is actually representable. So it is representable by a CNLWF algebra, even if rho bar is reducible. So this is like so he's giving a universal deformation ring of sort for every representation. And so the CNLWF algebra R rho bar square, which represents this functor, it's called universal frame deformation ring of rho bar. So you're sort of also lifting the basis. You're not just lifting representation, you're lifting basis along with it. That's the kind of interpretation. So this universal frame deformation ring exists for everything. So it has an added advantage of this view is that we can talk about local and global deformation rings of rho bar. Because earlier what happened is that even if rho bar is a deformation of global Galois group, it's a representation of global Galois group, and it is absolutely irreducible, it could happen that when you restrict it to some local Galois group, it becomes reducible. And then we cannot talk about deformation ring of this restriction. But here, there is no such problem. So you can, given a representation of global Galois group, you have frame deformation ring for global Galois group and frame deformation ring for every local Galois group as well. And so you have a map from the computed tensor product of frame deformation rings of local Galois group to the frame deformation ring of global Galois group. So this is the relation between them that you can exploit, and you can get a lot of interesting things, because there's no restriction on rho bar, so there's no restriction on anything, and you can actually freely work with these rings. And like the Allen's paper that I mentioned of Bigger Is T, he exploits this. There is a paper by Calgary and Allen. They also exploit this. It's on unramified or Fontaine measure, Boston strengthening of unramified Fontaine measure. So this certainly has a lot of advantages. You don't have to worry about existence, and you compare local and global deformation rings, which is already very handy. So to put on conditions locally, you can use both deformation rings. But a disadvantage, or whatever you can say, is that when rho bar is absolutely irreducible, the frame deformation ring becomes bigger than the universal deformation ring for obvious reasons. Because of this, if you want to use it for R is equal to T, these frame deformation rings are of not much use. For big R is equal to T. Of course, for small R is equal to T, you can take their quotients accordingly and manage. But if you want for big R is equal to T, these frame deformation rings are not that useful. For already when both rings exist, universal deformation ring and frame deformation ring, the frame deformation rings tend to be bigger than the universal deformation ring. A second direction that one could take is the study of pseudo representations. So we can use the study of pseudo representations developed by Chenevier, where you lift characteristic polynomial of rho bar rather than the representation rho bar itself. So to give some history, the pseudo representation term was first introduced by Wiles, where he was considering he had a notion of pseudo representation. It was simplified by Taylor, I think, in his thesis, or maybe a work that came right after his thesis. That was a notion of pseudo character, I think, which was like deforming trace-like functions. And Rouquier and Nissen sort of generalized this theory, but it still missed some cases. And Chenevier finally wrapped this whole thing up into this nice theory of pseudo representation. So it has this big history. But there, what you do is instead of lifting characteristic polynomial, instead of lifting rho bar itself, you lift characteristic polynomial or the coefficients of characteristic polynomial. So as an example, we'll see the pseudo representation of dimension 2. So if you have a topological ring R, a two-dimensional pseudo representation of G over R is a tuple T comma D from G to R of continuous functions, such that D is a homomorphism of groups from G to R star. T of 1 is 2. T of GH is T of HG for all G and H in G. And D of G times T of G inverse H plus T of GH is T of G times T of H for all G comma H in G. You would wonder that these seem a bit weird conditions, but as an example, if you have a representation rho from G to GL to R, then trace and determinant will give you a two-dimensional pseudo representation of G. So roughly speaking, whenever we say a pseudo representation of dimension 2, we mean a two-tuple of function which behave like trace and determinant of a function. They are not really trace and determinant of a representation. They are not really trace and determinant of an actual representation, but they behave like that. These properties, they should remind you, like this D is a homomorphism is a property of determinant, and these two properties, like they are the obvious properties of trace, like of a representation, that T of 1 is 2 and T of GH is T of HG. This third one is a bit tricky and that's crucial, and it is easy to verify. You can just write 2 by 2 matrices and you'll see this property. So as I said, that the idea is that when we say there's a pseudo representation of dimension 2, if it's a tuple of functions which behave like trace and determinant of a representation. It may not come from a representation, but their properties are very much like trace and determinant of a representation. So once you have this, you can just take any representation rho bar from G to GL2 of F, and we assume that G is satisfying the condition phi P, and we let D rho bar PS to be the functor from C, the category of sets, which sends a CNL WF algebra R with the two-dimensional pseudo representations T comma D, which lift trace rho bar comma determinant of rho bar. Because trace and determinant of a representation are obviously pseudo representations, this rho bar gives us this pseudo representation trace rho bar and determinant rho bar. And we can just look at pseudo representations lifting this pseudo representation rather than an actual representation lifting it. Navier's theorem says that this functor is representable by a CNL WF algebra. We call it R rho bar PS, and it's easy to see. I mean, this theorem is not that hard to conclude. This representability, you can just write it explicitly, at least in terms of, in the case of pseudo characters. And the nice thing about this is that if rho bar is absolutely irreducible, then this universal deformation ring of the pseudo representations is same as the universal deformation ring of the actual representation rho bar. So this theory, it really extends Mazur's theory. It really recovers Mazur's theory whenever rho bar is absolutely irreducible. So this is in a sense a nice thing to replace R rho bar unif by if you want to work with like R is T theorems, or you want big R is T and so on. This is like a natural thing to use instead of universal deformation ring of Mazur, because in rho bar we know that the two rings are the same when rho bar is absolutely irreducible. So I just gave an example of two-dimensional pseudo representation, but in general, n-dimensional pseudo representation does not have such a nice form. No, heuristically speaking, it is like deforming coefficients of characteristic polynomial, like we just did here, coefficients of characteristic polynomial of two-dimensional representations. But that this nice formula or this nice formulation in terms of tuples of functions is not there for n-dimensional pseudo representation. So that definition is a bit more complicated. But if P does not divide n factorial, then you have this theory of pseudo characters. Then the theory of pseudo representation becomes theory of pseudo characters, where you just lift functions which look like trace, and those are not that hard to define. So this is just an historical aside. But this pseudo representation theory really covers everything, so you can really use it. So the advantage, as I said, is that it's easy to define and work with, but the problem is that you're not working with actual representations anymore. You are working with these pseudo representations or coefficients of characteristic polynomials. So they may not always arise from representations, and that will cause a lot of problems, because most of the times we do like to work with actual representations. So that is like a disadvantage of this theory. So these are like two different directions that one can take in the future, if you want to go to reducible representations. So this is all that I want to say in this course. So thank you for being patient and listening to me. Thanks. There is a question in the chat. Is F still a finite field here? Yes, F is still a finite field here. Yeah, we are always over finite field, but you can go over a QP bar as far as I know. I don't know about F bar or Q bar, but you can certainly go to QP bar because you need CNL WF algebras. So you need some kind of periodic field or finite field. Okay, yeah, so I'm going to stop here. Thanks.
So let us thank the speaker for the wonderful course.